Welcome to the lecture number 33 of the course Quantum Mechanics and Molecular Spectroscopy. Until the last class, we looked at the rotational and vibrational transitions and the associated selection rules. Today, we are going to look at the electronic transitions and the possible selection rules for them. Electronic transitions happen between two different electronic states. Now, what does this two different electronic states mean? Two different electronic states mean for example, you have a molecule and one can define a electronic configuration. Even for atoms you can define electronic configuration, and let us suppose there are all filled orbitals using Pauli's exclusion principle or Aufbau principle combination of them. So, these are filled orbitals and these are unfilled orbitals. Then what I can do is that by applying energy or putting a photon, then I can go in presence of h nu, I can go from I have now transformed the electron, or I have replaced electron from the lowest from the highest occupied atomic orbital or molecular orbital to a lowest unoccupied. So, this is what we call as HOMO and this is LUMO. Of course, one does not have to restrict to this, one can go to LUMO +1 to higher energy levels as well. So, one can always excite from here to here to here to various levels, but this is the lowest energy transition. So, what I am doing in this case is that I am promoting an electron from an occupied level to an unoccupied level, that is the electronic transition. So, where you are displacing an electron from one orbital that is occupying to another orbital. These are called electronic transitions. By the way, when we have the absorption, electronic absorption, or what is known as the UV visible spectroscopy, in which you actually take out electron from one of the orbitals, occupied orbitals, and put it in the orbital that is unoccupied. Of course, you can also do from here to here. You can bring in the electrons that are lower than HOMO. So, many possibilities exist. So, electronic transitions are many such possibilities. One can have HOMO to LUMO or HOMO -1 to LUMO, or one can have HOMO to LUMO +1. So, this is HOMO -1, HOMO -2, HOMO -3. So, this is LUMO +1, LUMO +2, something like that. So, one can have many combinations, and you will see that this one, that is HOMO to LUMO, is the lowest energy possible transition. This is the lowest. Now, it turns out that when you do that, now if you use the build-up principle, and you can have a wave function called as psi ground, and this wave function will correspond to the electronic configuration. And one could have a psi excited as to electronic configuration. So, this is HOMO this is LOMO. Okay. Now there is one thing that I am trying to do here. Okay. If you see concentration HOMO and LUMO, what I have done, I have started from here and I have to this. Okay. The other possibility is this. Sorry. Okay. Now this state is represented by S is equal to 0. This state also is represented by S is equal to 0. Okay. This state is represented by S is equal to 1. Okay. So when we have S is equal to 0, this we call it as a singlet state. When you have S is equal to a singlet state, and when you have S is equal to 1, we have triplet state. Okay. Now S is equal to 0, S is equal to 1, triplet state, singlet state, this is because of the degeneracy of the wave functions. Okay. Now there are two things that are possible. Okay. So when you have psi g, okay, when you have this combination, okay, this is okay, and this is LOMO. So you could go to psi excited state in two possibilities. One is this, 1, 2. Where S is equal to 0, or one would have psi so that is S is equal to 1. So this is a singlet, this is a triplet. So one could have, this is also singlet. So when I go from psi ground to psi excited state, I can go from psi ground S0, S is equal to 0 to psi excited S is equal to 0, or I could go from a psi ground S is equal to 0 to psi excited S is equal to 1. So this is called singlet singlet transition, and this is called a singlet triplet. Okay. Now the exact wave function will depend on the molecule or atom in consideration. Okay. Now let us think of a transition moment integral. So TMI will be equal to integral psi ground, okay, mu psi excited d tau. That is going to be my transition moment integral. However, the way this transition moment integral has written has a problem, because you see there is something called Born open approximation. Okay. Now, what does Born open approximation say? It says that the electronic wave function parametrically depends on the nuclear coordinates. So, psi electronic is dependent on the electron coordinates, I would call it as i's, okay, and nuclear coordinates alphas. So, that means whenever the nucleus changes its position, the electronic wave function will change, and this gives rise to concept of potential energy surfaces. Therefore, your psi g, okay, will consist of two things. This will consist of psi g electronic multiplied by psi g nuclear, okay, and this comes out of the electronic transition or Born-Oppenheimer approximation. Therefore, it is similarly you have psi excited will have two possibilities, psi excited, okay, let me call it as electronic and psi excited nuclear, okay. So, this wave function that you use in the transition moment integral, it is bit more complicated. So, one can therefore write your TMI will be equal to psi g mu psi e, or rather other way around, d tau, in fact this should be equal to, the mu acts on psi g, psi e mu psi g d tau. But you know this is a Hermitian operator, so it does not really matter, okay, because overall the transition moment integral must be a the transition moment integral square, which is equal to, which is proportional to the probability of transition, is a square and it has to be a positive number, okay. So, it does not really matter whether, but technically this should be like this. So, this will be equal to your psi e will be equal to psi e electronic multiplied by psi e nuclear, and your psi g will be equal to psi g electronic multiplied by psi g nuclear, and the transition moment integral or the dipole moment vector can also be, see, you know, there is electronic charge distribution and there is a nuclear charge distribution. So, one can always write mu as a sum of mu e plus mu n d tau, okay. Now, I can separate this into two things. This is equal to integral psi e electronic, okay, psi e nuclear, okay, mu e, okay, rather I can psi g electronics psi g nuclear d tau plus integral. So, your total mu is written as mu e electronic plus mu nuclear, okay, and psi e electronic psi e nuclear mu n psi g electronic psi g nuclear d tau. Okay. So, now the total transition moment integral can be now divided into two such integrals. One because of the electronic dipole moment and other is the nuclear dipole. Okay. Now, evaluation of these two integrals is not very, it is going to be challenging. So, one makes another approximation called Condone approximation. So, essentially what are we looking at in this? Okay. We are looking at how the electronic wave function changes with respect to the nuclear coordinates. Okay. The electronic function does change with respect to nuclear coordinates. However, what we figure out is the dipole moment, the nuclear dipole moment or the dipole moment or let us say nuclear dipole moment mu n depends weakly on the electronic coordinates. So, that means this dependence on these coordinates is very weak, that is why we can neglect this term. And this neglection is called Condone approximation. So, your transition moment integral, okay. So, your TMI or other way to write it is the following, is that when you have integral mu electronic excited, mu electronic nuclear, mu E plus mu n psi ground electronic, psi ground nuclear d tau is equal to. Now, what in this what we do is mu n we equate goes to 0 and this is the Condone approximation. So, essentially the dipole moment is enhanced or contribution comes from only the electronic coordinates. So, this means what you have is mu E electronic, sorry, this must be psi E electronic not mu, psi E electronic, psi E nuclear, mu E, psi G electronic, psi G nuclear d tau. Now, we will see that the mu E electronic will only act on the psi E and psi G electronic. Okay. So, that means this will be equal to integral psi E electronic mu electronic psi G electronic d tau and integral over psi E nuclear psi G nuclear d tau prime, because the nuclear coordinates are under different the nuclear coordinates are different than the electronic coordinates. So, they are separate. So, these two are the integrals that need to evaluate it. So, for getting the electronic transitions one needs to evaluate these two integrals. Okay. Evaluation of these two integrals I will take up in the next lecture, we will stop it here now. Thank you.